네. Title UVM Testbench Consideration for Acceleration. The UVM has quickly become a universal standard for developing efficient and exhaustive verification environment for block level and system level design. One of the key principles of UVM is to develop and leverage a reusable verification component. One area of reuse that is gaining the momentum is the reuse of the verification component and environment between standard simulator and hardware acceleration. This paper focuses on techniques used to taking an existing UVM test bench and make the required changes to run with the hardware acceleration. If these considerations are made during the test bench development, migration to the hardware acceleration as performance option is much easier. This paper offers recommendations for making your UVM environment and component reusable for acceleration. Introduction. The UVM, the Universal Verification Methodology, UVM, has become widely adopted for development of complex verification environments, and many teams have begun to reuse the verification components and the environment for second and third generation design. When verification projects require very long simulation times, hardware acceleration can be leveraged to reduce the simulation time 4 hours to minutes or even days to hours. Ideally, a user would like to be able to run with the same UVM testbench TB in both simulation and hardware acceleration mode, ensuring that there is only one development stream to manage. Methodology adjustment discussed in this paper for development of the UVM verification environment will not have a negative performance impact for pure simulation and can have a positive impact when the design is moved to the acceleration hardware. Some of the performance considerations that are covered. Partitioning the top-level module so that the interfaces, DUT, and additional synthesizable components are in the module and the test bench is in a separated module. Separating your monitor into a collector for signal level information and a monitor for checking and coverage. Limiting access between the DUT and the test bench. Limit access to the DUT to the driver and collect only. Designing the environment to minimize the number of the transactions between the drivers and collectors at the last of the environment. Group transactions that can be executed without interaction with the last of the test bench. Creating synthesizable tasks to take transactions and drive signals, driver, and to resemble the transition from the signal level detail collector. This task can be moved to your interface and called from the driver and collector. Interfaces should be synthesizable so they can be partitioned to the hardware side. Removing time from the sequences. Use alternative method of specifying the delays between and within the sequences. A timing agent is introduced to execute delay sequences. These sequences executed in the interface during simulation and the hardware side during acceleration. Optimizing randomization of the transactions. Make sure that the unnecessary calls to randomized are not being executed. This call can have a significant impact on performance. 2. Is the hardware acceleration a good performance option for your UVM test bench? Before considering the acceleration, it is important to provide the environment with a reasonably long simulation runtime to check the significant portion of the time is being spent in the DUT code. Generally speaking, acceleration is not an efficient performance option for the environment where the test bench time is significant and the DUT time is small. However, when the transitioning to the subsystem and system level verification, the verification focus may not require the detailed verification features that are otherwise requisite at the block and high IP level. This means that even in cases where the simulation profile show that the test bench time is large and test bench optimization techniques can be applied, and those environments can be candidates for acceleration also. Acceleration is also not a good option if your simulation runtime are short. The main performance of the factors are to consider are described here and shown in the figure 1 below. The UVM Testbench runtime. This comprises any time spent in the simulator, including randomization of the test bench configuration and building the verification environment, configuring the DUT, driving random stimulus, checking received data and against the reference model, and sampling coverage. For long simulation, the test bench configuration and build time should be negligible since it only occurs once at the beginning of the simulation. 2. Software and hardware synchronizations. Signal and transactions that are sent between UVM Testbench and DUT initiate a synchronization event. Every interaction between the simulation and hardware incurs a delay. Additionally, the performance is impacted when data needs to be moved between the simulator and hardware. This overhead can be critical for performance. DUT runtime. This includes any aspect of the design and test bench that is executed on the acceleration hardware. Acceleration hardware is so fast, so it is important to move as much of the design and test bench to the hardware side as possible. This caveat is that anything on hardware side must be synthesizable. Figure 1. Relatively non-timed for simulation and acceleration. For example, if your profile simulation run and a test bench takes 25% of the simulation time, the DUT is 60% and the synchronization estimation is 15%. The maximum performance boost if the DUT is reduced to 0 is calculated as follows. Hardware time is 60%, 60% times 15% and 69%. Estimated speedup with our TV optimization 100 over 100 minus hardware time as 3.2 time. In this case, hardware acceleration may not be a good option. If the DUT time is increased, is 35% of the overhead is reduced to 10%. The maximum performance boost is improved. Hardware time 50% and 85%, 85% is 10 times 93.5%. Estimated speedup without additional TV optimization 100 over 65 is 15.4 times. Once you can that design is a good candidate for acceleration, there are adjustments that can be made to improve the performance beyond these numbers. Additional acceleration performance is achieved by reducing the time spent generating random stimulus and transferring data between the hardware side and the software side. 3. Partition your environment. It's recommended to partition your top-level module so that the DUT and additional synthesizer aspect of the environment are in the module, and the UVM Testbench is in a separate module. This should not impact simulation performance. Figure 2 shows a simplified verification environment partitioned to the support hardware acceleration. Figure 2 simplified verification environment with the DUT and TB separated. The top-level hardware module, hardware top, includes the DUT instance, a clock generator, interfaces that are connected between the test bench and DUT, and optional synthesizer memory component. The test bench module TB_top is simplified to include the UVM package, UVC component packages, and initial block to configuration start test. The Only purpose of the TB-top module is to use the UVM configuration database to configure the virtual interfaces called the run_test command. TB-top. Figure 3. Code example to simplify the TB_top module. 5. Implement a collector and a monitor. UVM recommends the inclusion of a monitor in each agent that passively samples signals on the DUT interface and assembles these information into transactions, correct coverage, and performing check. 4. Hardware acceleration and simulation. It is recommended to split monitor activity into signal and transaction level activities. This is similar to the UVM recommendation for creation of stimuli. For generating stimuli, UVM enforces the separation between the transaction level sequence and sequencer and the signal level activity driver. On the monitoring side, this separation is done by splitting the monitor into a low-level collector class and a high-level monitor, and that does transaction level coverage and checking. The collector is also a passive entity. It allows the interface-specific protocol to capture the transaction from signal data. The transactions are passed to the monitor by way of the UVM TLM port, and the monitor can do checking, sample coverage, and pass the transaction off the scoreboard and any other test bench component which may want access. Figure 5 recommends the UVC structure with the collector and monitor. And figure 6 is monitor collector interaction. The minimized interaction between the test bench and DUT. And when hardware acceleration is deployed, every interaction between the DUT and test bench requires synchronization event, and this adversely affects performance. It is important to limit the access between the test bench and the DUT to the driver and the collector only. That sounds intuitive, but it is very difficult to enforce this policy. Every interaction outside the driver and collector must be addressed when the design and the test benches are integrated to run on acceleration. The two common places where this is found is waiting for the signals to change inside the sequence and waiting for reset. A simple UVM clock and its reset agent and/or an interrupt agent can be added to the UVM test bench to limit access to these signals and generate event to the related to them. Next is 6. Driver and monitor adjustment. When user migrated from the simulation to the hardware acceleration, the first step is usually to the partition the UVM test bench to the simulator, move to the DUT to accelerate hardware side to verify the same test to count in both simulation and acceleration. This simple and signal-based solution takes less time to implement can produce result in a 5 times to the 20 times range depending on the implemented details of the test bench and DUT. With the transaction-based acceleration, part of the test bench is also moved to the hardware accelerator, and the interface between the test bench to the DUT through the task calls rather than individual signal transactions. This further reduces the number of the synchronization between the simulator and accelerator can produce results in the 30 to 300 times range. The performance boost is desirable, but requires that any portion of the test bench that goes to the hardware side is synthesizable. Development of your interface UVC driver usually includes implementation to a driver transfer task which converts the transaction to the series of the signal interaction over a period of time. These signals are connected to the DUT through a virtual interface. Similarly, the UVC monitor and collector typically includes a collector transfer task which capture signal level details from the virtual interfaces and assemble the transactions for checking and coverage analysis. Figure 7 illustrated the structure of the traditional UV signals that driven to the clock and in reference from the driver and collect class through the virtual interface handle. Figure 7 is the traditional UV structure. The for hardware acceleration is required to develop the driver transfer and collection drive transfer tasks to be synthesizable so they can move to the duty interface and included in the hardware module of the environment. Optionally, this method can be replaced in the interface for both simulation and acceleration. The only drawback to having these tasks inside the interface instead of driver class is that you cannot use UVM factory to override the default behavior of those tasks. This requirement overrides the driver transfer and the collect transfer tasks is rarely seen in the UVM environment. Figure 8 illustrates the structure of an accelerated UVC. The driver and collect core time-consuming interface tasks through a virtual interface handle. Signals are driven and clocks and signals are referenced directly inside the interface. The figure 8 accelerated UVC structure just so that now the section 7 clocks and reset. Clocks and resets are a very important part of designing for acceleration because the clock signal toggle frequency and can causes undesired synchronization event. It is recommended to develop implement a simple reusable UVM agent which uses the sequences to configure and start clocks. Initiation, reset, and execute delay sequences from the UVM Testbench. This implementation details of generating clocks and delays and resets will be handled in the system dialog interfaces and a clock generation module on the hardware side. The UVM clock and reset agent architecture is illustrated in Figure 9. Figure 9, UVM reusable clock and reset agent. The UVM code is below to demonstrate a simple reusable data items can be used to control the clock and reset generation in the duty. It has a control knob indicating clock period, reset information, and add a clock a cycle count for issuing a delay or timeout. Figure 10, UVM code for clock and reset data items. In the driver connect phase, it gets the clock and reset interface from the configuration database. Then in the run phase, it gets clock reset time items and uses the control information to execute clocking and reset tasks implemented in the interface. The system value code in Figure 11 below demonstrated the technique used in the driver to use the clock underscore reset underscore item information to code appropriate interface tasks. So Figure 11 is code for the clock and reset driver connect phase and run phase. And to ensure that the clock correctly recognizes the clock, ensuring the structure is placed inside a module, the control of clocks generated by that structure is handled from the interface that passes the appropriate control signals to the module. Handling out timeouts is a particular concern in an accelerated environment. It is often necessary to check that a particular event, transaction, or interrupt occurs within a certain time. If a clock's reference to the class-based side, this will require the frequent, expensive synchronization between the accelerator and simulator. To avoid this, a timer and sequence to drive it is built into the clock and reset UVC. The sequence returns once the set timeout has been reached and an event has been emitted. There is a field that can be set to cause an error if the timeout is reached before the end of the test. The timer can handle concurrent timeout requests even if they finish simultaneously. The system value code shown in these examples was simplified to demonstrate the techniques. If it is designed with the release in mind, this plugin listed UVM agent can be used within across as many projects and many teams. Step 8. Removing the timing from the sequences. For optimal performance, it is important to make sure that there is no timing in the test bench. This includes references to clock, sharp delays, and waiting on the transition on duty signals. Use alternative method to specify the delays within the sequences. The timing agent can execute delay sequences. These sequences execute in the interface during simulation and the hardware side during acceleration. The clock in the reset agent timer that counts clocks for timeouts can also wait for a number of the clock to execute before it returns while blocking the test bench from continuing execution. The clock and the reset agent also includes a sequence that can be configured to wait or not wait for user-defined delay of a variable number of clocks. This sequence can be used within a virtual sequence as shown in the system value code below. Figure 13 is virtual sequences using timing sequence. The code in the figure 12 represents the following code that might found in the virtual sequencer. The figure 12 virtual sequence body sample with virtual sequencer, and the figure the figure 12 virtual sequence body example with timing. Step 9. Randomization adjustment. Make sure the randomization controls are as simple as possible. Randomization requires when you are running a test with the acceleration. Make sure your interface UVC includes a sequence that does not call a randomize. The summary. Spending time upfront to the construct UVM environment that they are easily portable to the hardware accelerate can leave a big performance benefit in the end. The recommendations we make are enhanced to the UVM that meet the goal of using a single environment for simulation and hardware acceleration. Okay, today I read the UVM Testbench consideration for acceleration and the DVCON conference. Thank you for your time and see you next time.